In lesson 2, we're going to look at intercepts and zeros of polynomials. So the first thing we're going to look at is finding the intercepts of polynomials. So we have two different types of intercepts, the x-intercepts and the y-intercepts. X-intercepts is wherever the graph crosses the x-axis, which is why it's called the x-intercept. So it's where the graph crosses the x-axis. So if I had some polynomial where my graph crosses the x-axis is going to be all of the x-intercepts. So there could be no x-intercepts, the graph may never cross the x-axis, or there could be one, or there could be multiple x-intercepts. So in this particular picture, I have 3 x-intercepts. And if you notice, at these x-intercepts, y is equal to 0, and x is equal to something different. So if you ever wanted to find the x-intercepts algebraically, what you would do is set y equal to 0 and solve for x. And this is actually going to be a little bit more complicated than the y-intercepts, because when you think about polynomial equations, if you have to set y equal to 0, that means you could have to do some factoring or quadratic formula, completing the square, rational root theorem to be able to solve for x. But we'll look at how to do that a little bit later. But for right now, you just need to know that the x-intercepts is where the graph crosses the x-axis, and to find it, you would set y equal to 0. The y-intercepts can occur whenever the graph crosses the y-axis. So this is whenever the graph crosses the y-axis, which is why they're called the y-intercepts. And in order to figure out the y-intercepts, you do the opposite. So you would set x equal to 0 and solve for y, which is actually much easier than finding the x-intercepts, because if you have some polynomial, so let's say I have y equals ax squared plus bx plus c, or I have y equals ax to the third plus bx squared plus cx plus d. If you imagine plugging in 0 for every x, what's going to happen is you're going to be left only with these numbers at the end. So the y-intercepts are really just the constants. So y-intercepts equal the constant. So if you don't remember to set x equal to 0 and solve for y, basically it's just take the numbers at the end, and those are the y-intercepts. So for y-intercepts on a graph, you're only ever going to have one if you have any. So like you'll either have no y-intercepts or you'll just have one. It'll only cross the y-axis one time. So let's look at actually going through and finding the x and y intercepts. So for the first one here, let's find the x-intercepts. So we look at the x-axis and we identify any places where the graph crosses. And in this case, I have 3. So I have x equals -3, x equals 0, and x equals +3. You can also list these as coordinates if you want. So it would be -3, 0, 0, 0, and 3, 0, because it's when y equals 0. So notice that y is always equal to 0. And then for the y-intercept, I only have one, and it's where my graph crosses the y-axis, which is at y equals 0. So you can list it like that, or you can list it as a coordinate, which would be 0, 0. Then let's go over to the next graph here. So I have, again, 3 x-intercepts. It just so happens to work out that way. That's not always the case. But when I look at the x-axis, my graph crosses 3 times at x equals -2, x equals 0, and at x equals 1. So you can also list these as coordinates. So you can say -2, 0, 0, 0, and 1, 0. Again, notice that y is always equal to 0. And then for the y-intercept, again, it just so happens to work out that it's the same as the other graph. That's not always the case. But you get y equals 0 or the coordinate 0, 0. So on the next page, let's look at a little bit more with using the x-intercepts. So x-intercepts are really going to be one of the focuses for sketching graphs of polynomials, because the x-intercepts are also the zeros. So whenever you see the zeros of a polynomial, it really means the same thing as the x-intercepts, and vice versa. So if you see something about finding the x-intercepts, it's the same thing as finding the zeros. So when we go to graph that, whenever you have something with two or more zeros, that means you really have two or more x-intercepts. So basically, if you solve an equation and you get two or more zeros out, that means that you have two or more x-intercepts. So on your graph, this would look something like, okay, find two or more x-intercepts. So let's just say I have 5 different x-intercepts. So this means my graph could look something like this, where my graph we know has to be now an odd degree, and I know that it has to have a positive leading coefficient based on the leading coefficient test. So the zeros really do tell you a lot about your polynomial function. And also remember from Unit 8, when we talked about finding the zeros of a polynomial, we know that the number of zeros is equal to the degree of the polynomial. So if you have a situation with 1 0, that means that there has to be one x-intercept. So this would look something like this. So I have some graph, and it can only cross one time. So again, this tells us a little bit about the degree of the polynomial. It would have to be even degree, and in this case, the leading coefficient's positive because both ends are pointing up. And then the complex zeros are a little bit different, but complex zeros, remember, have to occur in conjugate pairs. So this would mean that you would have maybe two solutions in A plus BI form or A minus BI form. You'd have to have the conjugates. You'd have to have A plus BI as well as A minus BI. But whenever you have complex zeros, these are actually not going to show up on your graph as x-intercepts because these are complex numbers, where these would be one real zero, let's say, and two or more real zeros. So since these are real solutions, that means they show up on our x and y real coordinate plane. Where complex zeros, so let's say I had a picture with complex zeros. So let's say I solve some equation and I only got out complex numbers. What that means is my graph won't have any x-intercepts. It won't ever cross because I don't have any real number zeros. So that's kind of how the zeros tie into the x-intercepts. So just kind of keep that in mind. You could also have a combination. So basically I could have a situation where maybe I have two real zeros and two complex zeros. So what this would look like on my graph, though, is that I would only have two x-intercepts because, remember, your graph is representing the real number system. So this could look something like, okay, I have two real zeros, and then I have two complex zeros. So notice that my graph can't cross again. So I just kind of do this loop and bring it back down to represent those complex zeros. So it can't actually cross. So that's kind of just to show you, if when you solve equations and you get these zeros, well, how does that relate to the graph and the x-intercepts? So let's look at just two examples of these. So if I'm given the zeros as -3, 2, and 1, well, these are all real zeros. So that means I would have 3 x-intercepts. So you would start by just sketching a set of axes. So I would have -3, I would have 2, and I would have 1 as zeros. So then you can sketch. It doesn't matter for this particular, if all you know are the zeros, you don't know if the leading coefficient's negative or positive. So you can start down here if you want and then basically just connect. Or you could do the opposite. You could start up top and then you could connect all the zeros. So there's a couple different options, and since we don't know the equation of the polynomial, I don't know where to start from top or bottom. So either one is correct because we don't have enough information to know about the leading coefficient. But we do know based on our picture that this would have to be an odd degree polynomial. And then this one here, we have 4 different zeros. Notice we have 2 complex zeros, and notice that they do occur in conjugate pairs, so plus 3i minus 3i. That was a theorem that we learned in the last unit. So conjugate or complex numbers always occur in conjugate pairs when you're solving. So these are not going to represent any, so since these are complex, these aren't going to be x-intercepts, so not x-intercepts. Where these ones, the 0 and the 2, these are real numbers, so this means we would have 2 x-intercepts, one at 0, one at 2. So that means my graph, I would have something at 0, and then I would have another x-intercept at 2. And my graph is going to start either down below or above, and then it's going to do something like that example I showed you up top where it kind of does like another little loop, because if it just keeps going down, we really have 4 zeros, so that means there should be like 2 little bumps here. Now you could also have started up here and I've done something like that. So basically you just have to hit these twice. So notice this one, it was my second bump was in between the 2 zeros. But again, you just have to make sure you only hit these x-intercepts twice. We know that it has to be an even degree because either both ends are going up or both ends are going down, but we don't know the leading coefficient, so I don't know which picture is more accurate here. And then the last thing we want to look at is just that theorem. I've kind of been talking about this, but whenever we have a polynomial, whatever the degree of the polynomial is, so remember the highest exponent, that means that if we have a degree 4 polynomial, that means that we would have at most 4 real zeros. So at most, I'm going to put n in here because n is the degree. Real zeros, but we always have exactly n zeros if we're talking about the complex number system. So if we had a degree 3 polynomial, what that really means is we would have at most 3 x-intercepts because it's at most 3 real zeros, but we would have exactly 3 solutions. So if you were to solve this, that means that you would include complex numbers, so you would have to have exactly whatever the degree is. And then the turning points, if you look, the turning point would always be 1 less than the degree. So for example, if I had, let's say this one would have to be a degree 4, my turning points, there's 3 turning points. This one, let's say, is a degree 5, because there was 5 zeros. Then I had 4 turning points. So the degree is always 1 less than, or the number of turning points is always 1 less than the degree. So you'd represent that as n minus 1. So remember, real zeros really mean the x-intercepts, so maybe we should add that. And exactly n zeros if we're talking about the complex. So we have exactly n solutions and exactly, or at most, n x-intercepts. So this is just using that theorem. So name the number of zeros and the number of turning points of the graph. So in this one, you look at the degree. So the degree is 3. So that means we would have at most 2 turning points, because it's always one less. And we would have at most 3 x-intercepts, but exactly 3 solutions. So if you were to solve this, you would have exactly 3 solutions, because that means you would be including the a plus bi scenario, any kind of complex numbers. So then if you look at the next one here, the highest exponent is a 4. So this is a degree 4 polynomial. So that means we would have at most 3 turning points. And we would have at most 4 x-intercepts, because that means we could have at most 4 real solutions, but we would have exactly 4 solutions if we were to solve this. Because remember, our solutions include the complex numbers. So if you were to set this equation equal to 0 and solve it, you should be getting 4 answers. Now, some of them, you might get 2 that are complex numbers, because remember, they have to occur in conjugate pairs, which means that you would only have 2 x-intercepts, or 2 real numbers, meaning 2 x-intercepts. So the next thing is, well, how do you actually go about finding these zeros? So this is kind of just a summary for you of how do you actually find the zeros. So the zeros means when you set the equation equal to 0 and you solve for x, there's all different types of methods that may be used to find x. Quadratic factoring, difference of perfect squares, quadratic formula, completing the square, some of these other factoring techniques. You might have to use rational root theorem, and then, synthetic division to test the different possible zeros and narrow down which zeros actually work. And then the easiest way is to graph. But if you're trying to find the zeros graphically, again, remember that the zeros are really the x-intercepts, or the x-intercepts are really the real zeros. They're not all of the zeros, they're just the real zeros that you're going to see.